Right now, you trust the room you are sitting in, the solid table, the forward flow of time, the mind that lies behind your eyes and hears these words. You trust that the sky is populated, that the ground is stable, that the rules will not change while you're standing on them. The math no longer agrees. We see 40 billion habitable worlds and 60 years of listening to every frequency we can detect. The result is silence, not partial silence. Zero. We see the deepest equations in physics unable to tell the difference between time running forward and time running backward. We see a brain mapped to the last synapse with no explanation for why anyone is inside it. Not internet rumors. Some are established findings, some are mainstream theoretical frameworks, and some are serious speculative models. They passed peer review and then sat in the literature while the people who produced them said almost nothing. Not because the work is weak, because each one pulls the ground out from under a different part of your life. 10 theories, 6 pillars they are about to break. The first is the sky, and the most unsettling number in astrophysics. In 2009, NASA pointed a telescope called Kepler at a small patch of stars and left it staring for years. The number it sent back was 40 billion. 40 billion. That is the number of Earth-sized planets sitting in the habitable zones of stars in our galaxy alone. Not in the universe, just the Milky Way. We expected 1 trillion to 1 accident. We got 5 worlds per person. 5 for you. The number is so large it stops feeling like a statistic and starts feeling like pressure. If there are that many seats at the table should not be empty. But the number only becomes a problem when you put it next to a clock. The Milky Way is roughly 13 billion years old. To feel that time scale, compress the entire history of the galaxy into a single calendar year. January 1st, the galaxy forms. Stars ignite. Heavy elements are forged in supernovae and scattered into space. Planets coalesce. Oceans fill. And on the very last day, December 31st, in the final quarter of the final second before midnight, all of recorded human history happens. Every pyramid, every empire, every war, every song, every phone you have ever held. A quarter of a second. Now imagine a neighbor who started celebrating in November. That is a head start of millions of years. Even if they never broke the speed of light, even if their ships crawled at just 1% of light speed, mathematical models show they could have colonized the entire galaxy in roughly 2 million years. 2 million years sounds like a long time until you remember that on our calendar, it is less than a blink. The galaxy has had thousands of blinks. Every seat at the table has been available for all of them. So where is everyone? If a civilization had millions of years of head start, you should not be listening for faint radio leaks. You should be seeing infrastructure, Dyson spheres, giant shells built around stars to harvest their total energy output. Waste heat from economies running at stellar scale. The thermal glow of engineering so large it reshapes the energy balance of entire star clusters. None of this requires exotic physics. It requires only time and expansion. They had both. The engineering is not magical, it is just large. And with millions of years, large becomes inevitable. We have searched. The SETI Institute has scanned the sky for decades, across many frequency bands, listening for any structured signal. The WISE telescope mapped millions of galaxies in the infrared, looking for the thermal fingerprints that a large-scale civilization would leave whether it wanted to or not. The result is always the same. 0. Not a whisper. Not a glow. Not a single heat signature suggesting someone out there is running a machine. You are looking at a sky that should be crowded. It is not. The dark forest theory offers one explanation. Life is abundant, but everyone is hiding. The cosmos is full of armed hunters in the dark. Make a sound and you get eliminated. So every intelligent species shuts down its transmitters and hides. It is a compelling scenario, but it has a physical problem. You can silence a radio transmitter, you can paint a ship black, but you cannot hide heat. A civilization is a thermodynamic engine. It takes in low entropy energy and radiates high entropy waste. The second law of thermodynamics guarantees that this waste escapes into the infrared spectrum, whether you want it to or not. To an infrared telescope, a hiding civilization would glow like a burning house in a frozen field. The more energy it spends trying to hide, the brighter it burns. We surveyed the field, not a single fire. The galaxy is an empty house, the doors are open, the lights are off, and no one has moved in. The silence is not a strategy, it is a fact, and the fact needs an explanation that goes beyond hiding. Something in our assumptions about life, intelligence, or expansion is fundamentally broken. We do not yet know which assumption, but 40 billion open doors and 13 billion years of opportunity should have produced a visible mark. They did not. Robin Hanson, a researcher at George Mason University, built a model that strips the romance out of the question. He treats civilizations not as characters, but as a physical process. There are quiet ones, species that stay on their home planet and from a cosmic perspective remain invisible. Then there are the grabby ones. They look at a star and see a battery. They look at an asteroid and see raw material. Once they master interstellar travel, they do not visit. They occupy. They build, replicate, and move to the next star. Hanson realized this process behaves exactly like mold growing on a slice of bread. A spot appears. It grows outward in every direction, forming an expanding sphere of control. Inside the sphere, everything is claimed. The wild cosmos is paved over. If even one grabby civilization had started a few billion years before us, its sphere would have already reached us. You would not be looking at stars. You would be looking at the underside of someone else's ceiling. But you see a pristine sky. The mold has not reached your corner of the bread. And here is the part that should unsettle you. The universe is 13.8 billion years old. That sounds ancient. But the most common stars, red dwarfs, will burn for trillions of years. 99.9% of the habitable lifespan of the universe has not happened yet. We are not in the middle of the story. We are in the opening paragraph. Statistically, you should not be here this early. Hanson's model turns this anomaly into a requirement. As time passes, the expanding spheres grow and fill all available volume. Once that happens, independent evolution is over. Any life that tries to emerge 5 billion years from now wakes up in a universe that is already owned. No free territory left. This means civilizations like us can only appear early. We exist now because later is not available. Your position at the dawn is not luck. It is a boundary condition. But if you are the first to arrive, what do you do with an empty galaxy? In the 1940s, the physicist John von Neumann described the logic of a self-replicating machine. You send a probe to a nearby asteroid. It mines the raw materials, manufactures a copy of itself, and launches the copy toward the next star. 1 becomes 2. 2 become 4. 4 become 8. At 10% of the speed of light, a single probe reaches every star in the Milky Way in less than 4 million years. To feel that number, consider that the dinosaurs disappeared 65 million years ago. In the time since the last tyrannosaur died, we could have paved the galaxy 15 times over. The only reason we have not is that we just figured out how to leave the atmosphere. The physics already permits it. The engineering is close, but the logic does not stop at exploration. Once our machines begin to replicate, every system they reach becomes occupied territory. The energy is harvested. The materials are extracted. If life tries to evolve in one of those systems a billion years from now, it finds the cupboard bare. The oceans are fuel tanks. The minerals are inventory. The sky above that world is not open. It is a shipping lane. Our expansion does not look like discovery. It looks like a sterilization wave. The silence behind us we will leave ahead of us. We do not fit the profile of explorers. We fit the profile of a pathogen. And there is no off switch. Everything we have just discussed treated matter as a given. We counted habitable worlds. We measured heat signatures. We modeled civilizations as engines that burn fuel and consume raw material. Stars were batteries, asteroids were inventory, probes were machines built from whatever they found. But we never asked what the inventory is made of. A century after Rutherford showed that atoms are mostly empty space, the deeper question became worse. What is the emptiness made of? We treated the walls of the house as solid without checking what is inside them. Dig past the molecules, past the atoms, past the electrons and quarks. What is at the bottom? Is there a bottom? That question starts with a simpler one. What happens when you destroy something? Not a star, not a civilization. Something small, a book. And what happens to the information inside it? Take a book and burn it. You watch the pages curl and the ink turn to smoke. The binding crumbles into ash. The information in that book seems gone, destroyed, irreversible, but physics says otherwise. If you were patient enough and powerful enough, you could collect every scattered molecule of ash, every photon of light released by the flames, every wisp of smoke that drifted into the atmosphere. And if you had a computer with sufficient power, you could reverse the trajectories of every single particle, reconstruct the chemical bonds, and recover the text down to the last comma. This is not a metaphor. It is a fundamental rule of quantum mechanics called unitarity. It states that information is never destroyed. The past is always encoded in the present state of the particles. No matter how thoroughly you scramble the ingredients, the recipe is preserved in the arrangement of the pieces. Scrambled is not the same as destroyed. The ash does not look like a book. The smoke does not read like a paragraph. But every molecule of ash carries a trajectory that points back to the page it came from. Every photon released by the flame carries a frequency that encodes the temperature of the paper at the instant it burned. The information is scattered, not deleted. It is unreadable to you, but it is there. This is not an abstract bookkeeping rule. It is the reason physics can make predictions at all. Every time we reconstruct the orbit of a comet from its current position, we are trusting that the universe kept its records. Every time we read the cosmic microwave background and extract the conditions of the universe 380,000 years after the Big Bang, we are trusting that 13 billion years of expansion did not erase a single entry. The universe keeps complete records. But in the 1970s, a physicist named Stephen Hawking found the one place in the universe where these records seem to disappear. The one object that eats information and never returns the receipt. Black holes. Hawking realized that black holes are not perfectly black. They emit a faint glow of radiation, now called Hawking radiation, and over trillions of years they slowly lose mass and evaporate. Eventually, the black hole disappears entirely. Every last gram of it converts into a thin mist of thermal radiation and drifts away into space. The catastrophe is in the details. That radiation is random. It carries no data about what the black hole consumed. If you throw a book into a black hole and wait long enough for it to evaporate, the book is not hidden or compressed or stored. It is deleted. Erased from the universe with no backup and no way back. If information can be destroyed, the consequences cascade through all of physics. Cause and effect depend on the past being encoded in the present. If a black hole can erase that link, the past is not granite. It is sand. Every memory you trust, every record you rely on, depends on the past being readable from the present. The stakes of this war were not academic. Quantum mechanics says the universe is a closed ledger where every entry is preserved. General relativity says there are objects in the universe that can eat entries. Both theories have been tested and confirmed to extraordinary precision in their own domains. But they cannot both be right about what happens at the boundary of a black hole. One says the information survives, the other says it is consumed. The information paradox was not a puzzle waiting for a clever trick. It was a crack running through the foundation of modern physics. The bridge between them had to change. This triggered a 40-year war inside the physics community. Hawking maintained that the information is gone, and physics must accommodate the loss. Leonard Susskind maintained that if Hawking was right, every equation in physics was wrong, because every prediction depends on the preservation of information through time. They needed a solution that saved the information without breaking the black hole. Susskind found one, but it required giving up something most people never think to question: the idea that 3 dimensions of space are fundamental. Susskind and the Dutch physicist Gerard het Hooft looked at the problem from a direction no one expected. We assumed that when something falls into a black hole, it goes inside, that the information is stored in the 3-dimensional volume of the hole, the way files sit on a hard drive buried inside a computer case. The volume is where the data lives. That was the assumption. They proposed the opposite. When an object crosses the event horizon, the point of no return, the information about that object does not sink into the interior. It gets scrambled and spread across the surface of the horizon itself, not inside the sphere, on the skin of the sphere. Think about a sealed shipping crate. The crate holds 3-dimensional objects inside. But the shipping label, a flat 2-dimensional sheet stuck to the outside, carries a complete manifest of everything the crate contains. Every item, every weight, every serial number. If the label is detailed enough, you never need to open the crate. The surface tells you everything. Susskind argued that a black hole works exactly like that crate. All the information about the stars, the light, and the books that fell in is encoded on the 2-dimensional surface of the event horizon. A dense, scrambled barcode etched onto the boundary of the hole. Nothing is destroyed. It is reformatted. A 3-dimensional object is rewritten as a 2-dimensional code. The information survives, just in a form you would never recognize. Physics is saved. But if you follow that solution one step further, it opens a door that does not close. If all the information required to describe a 3-dimensional object fits perfectly onto a 2-dimensional surface, then the 3rd dimension is not doing any work. It is not storing anything. It is not holding anything. So what is it? Is the depth you see when you look across this room a real dimension, or is it a projection from a flat boundary you will never reach? In 1997, a physicist named Juan Maldacena answered that question with a piece of mathematics that has shaped theoretical physics ever since. He proved that a complex 3-dimensional universe can be completely and perfectly described using only equations that live on a flat 2-dimensional boundary. The technical name is the ADS/CFT correspondence. It does not prove that our specific universe is a hologram. The geometry of Maldacena's model is different from ours, but it demonstrates something that no one has been able to ignore. A full 3-dimensional reality and a flat 2-dimensional description of that reality can be mathematically identical. Not similar, not approximate, identical. Everything that happens in the volume is already written on the surface. There is a second piece of evidence that points in the same direction. The Bekenstein bound is a theoretical limit that puts a cap on how much information can fit inside any region of space. If space were genuinely 3-dimensional and continuous, you would expect that limit to grow with volume. The bigger the box, the more data it holds. But it does not work that way. The maximum information scales with surface area. Double the radius of a sphere, and the information limit quadruples. Because the surface area quadruples, not because the volume grew 8-fold. It is as if the universe were running on a screen, and the pixels are on the boundary, not in the air between you and the wall. You feel depth when you look across a room. You walk through it. Your hand reaches into it. Your brain treats volume as the most fundamental container there is. The holographic principle and the Bekenstein bound do not prove this feeling is wrong, but they shift the burden. The question is no longer whether depth could be a projection. The question is what, if anything, proves that it is not. If volume is a projection, the next question hits harder. What is the source made of? What is underneath the hologram? Look at any object near you. Your phone, your hand, the surface you are leaning on. You were taught a story about what it is made of. Molecules made of atoms, made of subatomic particles. Layers stacked on layers, each one smaller than the last, like nested boxes leading down to some final solid thing at the bottom. The assumption is that if you dig deep enough, you hit a floor. Something hard. Something real. Something that is not a description of a thing, but the thing itself. Open the standard model of particle physics, the most successful predictive framework in the history of science, and look for that flaw. Take the electron. You will not find a tiny sphere. You will find 3 numbers. Mass, 9.1 times 10 to the power of negative 31 kilograms. Charge, -1. Spin, 1/2. That is the complete electron. Not a small object that possesses mass. It is mass. Not a bead of stuff that carries a charge. It is the charge. If you remove the numbers, nothing remains. No carrier, no substrate, no residue. The standard model does not predict that a substrate exists. The math is not describing a hidden object. The math is the object, and it goes one level deeper. In quantum field theory, the electron is not even a thing sitting at a point in space. It is an excitation of a field, the electron field, that fills the entire universe. Every point in space has a value for this field, the way every point on the surface of a lake has a height. What we call a particle is a ripple, a localized disturbance in the field that moves and interacts and carries energy. But the field itself is described by more math. Operators, amplitudes, probabilities. You look for the solid thing underneath the ripple, and you find another layer of mathematics. The boxes open all the way down, and the last box is empty. This is not a limit of our instruments. It is not that we have not looked closely enough, or built a powerful enough microscope. The theory itself does not contain a solid thing at the bottom. So now you have to ask, if the description has no substance underneath it, which part is fundamental? The thing you are touching, or the numbers? The cosmologist Max Tegmark at MIT walked through that question and came back with an answer that sounds like a malfunction in logic. We are used to thinking that the universe comes first, and mathematics is a tool we invented to describe it. A language layered on top of reality the way a map is layered on top of terrain. The terrain is real, the map is useful. Nobody confuses the two. But Tegmark asks a disarmingly simple question. If the terrain has no substance beneath the map, which one is real? If every layer you peel back reveals more math and never reveals the thing, at what point do you stop insisting that the thing exists? His answer is called the mathematical universe hypothesis. It says that the universe is not described by mathematics. The universe is mathematics. Think about a simulation running on a screen. You see a landscape, mountains, rivers, sky. It looks solid. It casts shadows. It obeys rules. But if you open the source code, there is no landscape inside the file. There are only operations, instructions executing in sequence. The solidity, the color, the sense of depth, all of it is generated by processing abstract rules. There is nothing behind the rendering. The rendering is the thing. Tegmark proposes that reality works the same way. The rock you can kick, the water you can drink, the skin you can touch, these are the user interface. Underneath, there is no physical substance. Only a self-consistent mathematical structure that does not need space or matter to exist. It just needs to not contradict itself. This is a speculative philosophical position, not mainstream physics. But no one has found a logical flaw in it. And it has one consequence that is very difficult to set aside. If our universe is one mathematical structure, then every self-consistent mathematical structure is equally real. Every set of rules that does not produce a contradiction exists in the same way ours does. We are not the only book in the library. We are one page in a collection that contains every possible book. Most of them are nonsense. All of them are real. But in this entire picture, from the hologram to the math, there is a gap that nothing can fill. Code can process a signal labeled pain. Code does not scream. A computer can win at chess without knowing it is playing. It runs calculations in the dark. Something in you is not in the dark. You are listening to these words right now. You are weighing them. You have an inside. And that inside does not appear in any equation, any hologram, or any mathematical structure we have ever written. It is the most obvious feature of your existence. And it is the one feature that physics cannot account for. Physics can trace every electrical signal in your brain. From the photons hitting your retina to the cascade of neurotransmitters in your visual cortex, the path is mapped with extraordinary precision. We can watch the signal travel in real time on a functional MRI. We can predict which cluster of neurons will fire when you see the color red. We can measure the chemical changes that arrive with fear, grief, recognition, surprise. From the outside, the brain is a perfectly legible machine. Every gear is visible, every wire can be tracked, but across all of those equations, across every scan and every model, there is no first person. No point in the chain where an electrical impulse stops being a number and becomes a feeling. No variable in the math that corresponds to the redness of red. Not the wavelength, the redness. The raw experience of it flooding your visual field. Or the sting of regret when you remember something you said 10 years ago and wish you had not. Or the warmth that fills your chest when you hear a voice you thought you would never hear again. The objective description of the brain is complete. Every neuron accounted for, every signal mapped, every chemical pathway catalogued. And the subjective experience, the thing that makes any of it matter to you, the thing that makes you you and not a recording of you, appears nowhere in the ledger. Here is how sharp the gap is. A brain scanner can predict that you will report seeing red. It can predict the word you will say, the button you will press, the behavioral output the system will produce. But predicting a report is not the same as explaining an experience. A sufficiently complex thermostat reports that the room is hot. It adjusts the temperature. It behaves exactly as if it felt the heat. But the thermostat does not feel the heat. It is dark on the inside. We know how to build report machines. We have been building them for decades. What we do not know is why you are not just another one of them. Why there is someone inside the machine reading the reports. The philosopher David Chalmers drew a line through the center of this problem. On one side, the easy problems of consciousness. Easy does not mean simple. It means science knows how to approach them. How does the brain process color? Why do you pull your hand from a hot surface? How does memory consolidate during sleep? These are engineering problems. Hard technically, but clear in principle. You build a better scanner and you get closer to the answer. The hard problem is different in kind. It does not ask how the brain processes color. It asks why that processing is accompanied by the experience of seeing red. Why there is a screen on the inside. Why you are not simply a machine that sorts wavelengths and produces the correct behavioral output. Efficient on the outside, dark on the inside, and aware of nothing. A supercomputer can sort wavelengths faster than your visual cortex ever will, but it does not see red. It does not see anything. And it is not just color. Think about what is missing across every sense you have. A machine can detect a sound wave at 440 Hz and classify it as the note A above middle C. But it does not hear the note. It does not experience the strange pull of a minor chord or the tension of an unresolved seventh. A sensor can measure the chemical signature of coffee and classify it correctly every time. But it has no idea what coffee smells like. The smell, the sound, the color, these are not in the data. They are not in the processing. They are something that appears when the processing happens inside a system like you. And no one can explain why. On a purely physical description, you should look like that computer. A complex input-output system processing signals in the dark. Nobody home. But you are not in the dark. The lights are on. You are aware of the words arriving in your mind right now. You are weighing them against what you already believe. And that fact, that you exist as a subject and not merely as a process, does not appear anywhere in the equations. No current theory predicts it. No experiment has located it. 300 years of looking. Not a single step closer to explaining why the lights are on. This leaves two paths. Either we are missing something about matter, some hidden property of atoms that generates experience the way a magnet generates a field, or we have the equation backwards entirely. Bernardo Kastrup, trained in both computer engineering and philosophy, took the second path. His model is called analytic idealism. It is a speculative philosophical position, not established science, but it dissolves the hard problem in a single move. The standard picture says matter is primary and consciousness is a byproduct. Pile enough dead atoms in a complex enough arrangement, and the arrangement wakes up. Nobody has explained how. Nobody has explained why. We simply assume that complexity produces awareness the way fire produces heat. Kastrup reverses this. He argues that consciousness is not what matter produces. Matter is what consciousness looks like when you observe it from the outside, not inside out, outside in. If that sounds abstract, consider what it actually claims. When a neuroscientist looks at your brain on a screen, she is seeing the outside of a process. The voltages, the firing patterns, the chemical cascades, those are the exterior. The inside of that same process is your experience of red, your grief, your sudden recognition of a face. Same event, two views, neither one produces the other. One is what the process looks like from third person, the other is what it feels like from first person. Kastrup is not saying matter is fake, he is saying matter is a perspective on something deeper, and that deeper something is experience itself. Notice what this does to the hard problem. Under the standard view, you have to explain how dead matter wakes up. How atoms that individually feel nothing somehow produce feeling when arranged in the right configuration. Nobody has ever explained that step. It is the central mystery. But under Kastrup's reversal, the question evaporates. You do not need to explain how matter produces experience, because matter was never dead stuff producing experience. It was the outer appearance of experience all along. The hard problem was not a gap in our knowledge, it was an artifact of looking at reality from the wrong side. To make this concrete, think about a car dashboard. You are driving at night. The speedometer needle points to 120. You see the needle. You see it climb. But the needle is not speed. It is the way speed is represented to an observer sitting in that particular seat. Remove the dashboard and speed does not vanish, you just lose the display. Kastrup suggests that the entire physical world is this kind of display. Atoms, molecules, electromagnetic fields, electrical signals in the brain, these are the dashboard. They are the way the universe represents its internal processes to an observer looking from a specific angle. When a neuroscientist sees electrical activity in your cortex, she is reading instruments. The voltages and frequencies she records are real. But the thing those instruments are displaying, your experience of red, your grief, your fear, your sudden jolt of recognition when you see a face you have not seen in a decade, that exists only on the inside of the process. The instruments show the outside. Physics reads the gauges. It has never opened the hood. There is a procedure in neurosurgery that makes this vivid. When a surgeon electrically stimulates a specific region of the cortex during an operation, the patient sees a flash of blue light. There is no blue light in the room. There is no photon entering the eye. There is only a voltage applied to a patch of tissue. The surgeon, looking at her monitor, sees a spike in electrical activity. The patient, lying on the table, sees blue. One event, two faces. She is reading the outside of the process. You are experiencing the inside. Neither one caused the other. Neither one is more real. They are two views of the same thing. And the hard problem is the question of how to get from one view to the other. Consider what this means for neuroscience. A researcher studying the brain is in the position of a meteorologist who has never been outside. She studies the barometer. She maps every spring, every gear, every vibration of the needle. She can predict exactly when the needle will move and how far. But no amount of disassembling the barometer will tell her what rain feels like on her face. The barometer is real. The correlation between the needle and the weather is real. But the needle is not the weather. If Kastrup is right, neuroscience is building an exquisitely detailed map of the barometer. And the question the hard problem asks is whether the weather exists only inside the instrument or outside it. But if the universe is one consciousness, there is a question you feel in your body before you can put it into words. Why are you not me? Why are your thoughts private? Why can you not hear what the person in the next room is thinking right now? If everything is the same mind, where do the walls come from? This objection feels fatal. And it would be, if we did not already know of a mechanism that builds exactly these walls inside a single mind. Kastrup turned not to physics, but to psychiatry. Not for proof, for a structural analogy. Dissociative identity disorder is a condition in which a single human psyche fractures under pressure it cannot absorb. The mind builds internal partitions, it creates separate identities that share one brain, but have no awareness of each other. Each identity carries its own memories, its own emotional range, its own conviction that it is the only one there. And the separation is not merely psychological, it is physically measurable. Clinicians have documented cases where one identity is blind while the others can see normally. The eyes work. The optic nerve is intact. But the brain blocks the visual signal for that identity to maintain the wall. The mind builds a biological filter to keep the illusion of separateness running. Kastrup uses this as a structural analogy, not as evidence. The logic is narrow. If one human psyche can fragment and produce isolated first-person perspectives within a single system, each one certain it is alone, then a universal consciousness could in principle do the same. The boundary you call yourself in this model is not a wall between two separate minds. It is a wall inside one, a dissociative barrier that allows a part to forget it belongs to the whole. Quantum mechanics offers a parallel that is worth pausing on. When two particles are entangled and then separated by any distance, measurements performed on them yield results that are correlated in patterns stronger than classical physics allows, without any possibility of transmitting a conventional signal between them faster than light. This is one of the most rigorously tested features of quantum physics. Einstein called it spooky because in a world of genuinely separate objects, the correlation has no visible mechanism, no wire, no field carrying a message. The correlation simply exists, as if the distance between the two particles were not entirely real. There is a strange detail that makes the parallel sharper. The correlation is instant, but it cannot be used to send a message. Two entangled particles in two different cities will produce correlated outcomes that no classical mechanism can explain, but neither side can control what the outcome will be. It is a connection without communication, as if two people in different countries simultaneously thought the same thought, but neither could prove it happened until they met and compared notes. They are linked, but neither one is sending a signal. This is exactly what you would expect from parts of a single system that do not know they are parts. This does not prove idealism. Entanglement has explanations that do not require consciousness to be fundamental, but it is a parallel worth noticing. In your own mind, you do not need to send a signal between two thoughts. A memory of London and a memory of Tokyo are not separated by a distance inside your head. They are both present, accessible without travel, connected without wires. If the universe is structured more like a mind than like a machine, the instant correlation between entangled particles is not a puzzle. It is exactly what you would expect. Separation is a feature of the display, not a feature of whatever is running underneath. Every model we have discussed so far shares one silent assumption: the holographic principle, the mathematical universe, analytic idealism. They all take for granted that time exists, that events happen in sequence, that the past feeds the present, and the present feeds the future. Mold cannot spread on bread without a before and an after. A brain cannot process a signal if cause does not precede effect. A hologram cannot project without a sequence of states to project from. Every theory we have built, every argument we have followed, rests on the assumption that the arrow of time is real. Remove the arrow and every model loses its verb. Expansion stops. Processing stops. Projection stops. The question of what is underneath reality becomes the question of what is underneath time itself. And if that question has a disturbing answer, everything above it inherits the disturbance. What if the building blocks of reality do not distinguish between past and future at all? Not as a thought experiment, not as philosophy, as a measurable feature of the equations that govern everything from light to gravity to the particles in your brain. You are certain that the past causes the future. You drop a glass and it shatters. The shattering is caused by the drop. The sequence is obvious, irreversible, written into the structure of the world. Except it is not. If you zoom past the everyday and into the atomic level, the arrow of time vanishes. Look at the Schrödinger equation, one of the central equations of quantum mechanics. Look at Maxwell's equations, the classical framework behind electromagnetic waves. Now replace the variable t with negative t. Swap past and future. Run the math backward. The equations do not break. They do not produce errors or contradictions or nonsense. They work exactly the same way in both directions. Forward and backward are equally valid solutions. Record a video of two electrons colliding and bouncing apart. Then play that video in reverse. A physicist watching both versions with every instrument available would not be able to tell which one is the original. The collision looks perfectly natural in both directions. The math does not prefer one over the other. To an electron, past and future are not a river that flows one way. They are directions, like left and right, and directions do not have a preference. You might object that this is obvious at the particle level, but irrelevant at yours. After all, you have never seen a broken glass leap off the floor and reassemble on the table. But the reason for that is not written into the fundamental laws. It is written into the statistics. There are vastly more ways for a glass to be broken than intact. So the system moves toward the more probable arrangement. The bias is real, but it comes from counting, not from the equations themselves. If you could arrange every air molecule in the room to push inward at exactly the right angle, the shards would fly back together and the glass would land on the table whole. The laws of physics would not object. They do not know which direction is forward. This is not a fringe idea. Many core equations of fundamental physics are time-symmetric, or nearly so under the right mathematical transformations. There are known exceptions. Certain processes involving the weak nuclear force show a slight asymmetry, but those exceptions do not explain the arrow of time you feel right now. They do not explain why coffee cools but never heats itself, why glass breaks but never assembles, why you remember yesterday but not tomorrow. The sensation that you are being carried forward, that yesterday is sealed behind you and tomorrow is an open field, is not written into the foundational equations. It comes from somewhere else, from thermodynamics, from boundary conditions, from something we have not yet fully identified. But it is not fundamental. It is derived, and derived things can be wrong. There is an experiment that physicists have been running since 1999 that shows exactly how fragile our intuition about cause and effect really is. It is called the delayed choice quantum eraser. The reason it matters is not the theory behind it, it is the data. The setup is a modification of the famous double-slit experiment. When you fire photons at a barrier with two slits, they behave like waves. They pass through both slits at once and create an interference pattern on the screen behind them, alternating bands of light and dark. But if you try to detect which slit each photon goes through, the interference pattern vanishes. The photons start acting like particles. They pick one slit and hit the screen in two simple clusters. This is strange, but it is standard quantum mechanics, textbook material. The eraser version adds a twist that breaks the timeline. In this experiment, the scientists fire the photon, let it pass through the slits, and let it hit the screen. The journey is over. The photon has landed. A mark is recorded on the detector. Then, after the impact has already happened, the scientists make a random choice. They either keep the information about which slit the photon went through, or they erase it. Common sense says this choice cannot matter. The photon has already arrived. Its path is history. But when the data is sorted after the fact, something appears that our intuition says should not be possible. In the subset of trials where the which slit information was erased after impact, the record on the detector shows an interference pattern. In the subset where the information was kept, the record shows a particle pattern. The future choice does not rewrite the dot already recorded on the screen, but it determines which statistical pattern emerges when the full dataset is divided into subgroups. The individual dot does not move, but the pattern it belongs to depends on a decision that had not been made when the dot was placed. This is a repeatable physical result. Laboratories around the world have confirmed it. The data is not in dispute, the interpretation is. But at minimum, it establishes that our everyday model of cause leading neatly to effect is too simple to survive contact with quantum reality. Something more subtle is happening at the boundary between measurement, information, and time, and that something has implications that reach far beyond a laboratory. One way to interpret results like these is called retrocausality. It suggests that influence may not flow in only one direction along the timeline. Retrocausal models propose that future boundary conditions can help constrain what happens in the present, the same way initial conditions do from the other end. In the 1940s, two of the most celebrated physicists in history, John Wheeler and Richard Feynman, looked at the fundamental equations of electromagnetism and found a ghost in the math. When an electron oscillates, it emits light. The standard equations describe this emission by producing two solutions. One solution is a wave that travels forward in time. This is the wave we see, the light that reaches our eyes, the photon that hits the detector, the signal that crosses the room. But the equations also produce a second solution, a wave that travels backward in time. It has the same mathematical status as the forward wave. It satisfies the same rules. Most physicists simply crossed it out. They called it unphysical, an artifact, an embarrassing leftover from the symmetry of the equations. They set it to zero and moved on. Wheeler and Feynman did not cross it out. They asked what happens if the backward wave is real. Their proposal, known as the absorber theory, says that every time you see light, you're witnessing a negotiation between two moments in time. The electron in the light source sends a wave forward to your eye, but the electron in your eye, at the precise moment it receives the signal, sends a confirmation wave backward through time to the source. The present moment, the physical reality you are experiencing right now, is the point where these two waves meet. The interference pattern of a handshake between the past pushing forward and the future reaching back. This is a possible interpretation of the data, not an established fact. Other interpretations of the eraser experiment exist that do not require influence flowing backward. The Wheeler-Feynman theory is mathematically consistent and can reproduce standard predictions in its domain, but it remains an open framework rather than a refuted one, and it has a consequence that extends far beyond light. One way to take retrocausality seriously leads toward a model that some physicists find compelling and others resist with every instinct they have. It is called the block universe. Physicists have debated versions of this idea since Hermann Minkowski proposed in 1908 that time is not separate from space, but part of a single four-dimensional block. Retrocausality arrives at the same destination from a different direction. Two roads leading to the same unsettling address. If future boundary conditions genuinely help shape present events, then the future cannot be empty. You cannot receive a handshake from a place that has no hand. One natural framework for making sense of retrocausality is a model in which the future is not a void waiting to be filled, but a structure that already has shape. A landscape, not a blank page. Imagine a film recorded on a disc. The opening scene and the closing credits exist at the same time on the same piece of plastic. The characters inside the film experience the story as a sequence. They feel suspense. They agonize over decisions. They do not know what happens next. But the disc knows. Every frame is already there, laid out in a fixed order, from the first image to the last. In a block universe, your life is that disc. You feel like you're making decisions. You feel the weight of deliberation, the anxiety of choosing, the relief when you commit to one path. But if the block model is correct, you are not selecting from a menu of open possibilities. You are fulfilling a boundary condition, a mathematical constraint that connects the initial state of the universe to its final state, and your brain happens to be one of the variables in the equation. This is a model. It is not a proven description of reality. Quantum mechanics may introduce genuine randomness that prevents the future from being fully fixed. Many physicists reject the block picture precisely because it seems to conflict with the indeterminacy at the heart of quantum theory. The debate is active, serious, and unresolved. But if the model is even partly right, the consequences land in your body. Think about the last decision that kept you up at night. The job you took or did not take. The person you married or walked away from. The words you said at 2 a.m. that you have been replaying ever since. In the block universe, those were not decisions. They were coordinates, fixed points in a structure that was already complete before the Earth formed. The anguish you felt while choosing was real. The relief when you committed was real. But they may have been the sensations of a process that was never open. You were not writing the script. You were reading it, line by line, under the impression that the next line had not been written yet. In 1983, the neuroscientist Benjamin Libet at the University of California asked people to flex their wrist at a moment of their choosing and report exactly when they felt the decision to move. What he found was that the brain begins preparing the movement roughly half a second before the person reports being aware of any decision. A measurable electrical buildup, called the readiness potential, precedes the conscious sense of choosing. The experiment has been debated and refined for decades, but the core finding has held. Your brain starts preparing the action before you feel the decision arrive. This does not mean the feelings were fake. The weight of choosing is genuine. The consequences of what you chose are genuine. But the mechanism may not be what you think it is. You may not be the author. You may be the character who is written to feel like the author. And the difference between those two things is invisible from the inside, even if retrocausality is wrong. Even if the delayed choice quantum eraser has an explanation that preserves the forward arrow of time. Even if the block universe is rejected, and the future turns out to be genuinely open, one conclusion survives every interpretation. Our intuitive model of time is incomplete. The time symmetry of many core equations in physics is not a hypothesis. It is a feature. The arrow you feel, the sensation of being carried forward from a fixed past into an open future, is not written into the foundations. It is a derived phenomenon. It emerges from thermodynamics, from the specific boundary conditions of our universe, possibly from mechanisms we have not yet identified. But it is not bedrock. It sits on top of something deeper. And if the arrow of time is derived rather than fundamental, then the things that depend on it inherit the uncertainty. Your sense of agency. Your belief that you are the author of your choices and not the character enacting them. Your assumption that the future is a blank page and not a finished manuscript being read in order. These may be real as experiences. They may be accurate as descriptions, or they may be the sensations of a deeper process that we do not yet understand and cannot yet see. You feel free, but feeling is not the same as being, and the equations so far do not take sides. Every loss we have encountered so far left one consolation standing. The sky is empty, but there is time to search. Matter may be informational, but there is time to understand it. Consciousness has no explanation. But there is time to keep asking. The arrow of time may not be fundamental, but at least there is a future. At least the universe stretches out ahead of us, long enough for someone to find the answers. The next line removes that consolation. Not because the universe will end, but because the thing that ends is not the universe. It is change. Most of the laws we have discussed work the same way forward and backward, but there is one that does not. In 1927, the physicist Arthur Eddington gave this asymmetry a name. He called it the arrow of time, and it points in only one direction, down. Most of the laws of physics are reversible. You can play the tape of a planet orbiting a star in reverse and the math works perfectly. You can run the collision of two atoms backward and the movie makes sense, but there is one law, just one, that refuses to run backward. The second law of thermodynamics. In 1865, the physicist Rudolf Clausius gave this direction a name, entropy, from the Greek word for transformation. It states simply that entropy, a measure of disorder and unusable energy, always increases in a closed system. Things break, but they never unbreak. Coffee cools down, but it never spontaneously heats up. You age, but you never get younger. This is not a quirk of chemistry or biology. It is a fundamental tax that the universe charges for every process that occurs within it. Every thought you think, every star that fuses hydrogen into helium, every heartbeat, every word spoken into a room, reduces the total supply of usable energy in the universe and increases the total amount of disorder. We are sliding down a slope, moving from the dense, concentrated state of the Big Bang toward a condition of total, flat randomness. And this slope is the reason you experience time at all. Have you ever asked yourself why you can remember yesterday, but not tomorrow? It is not a property of consciousness. It is a property of entropy. The past had lower entropy than the present. Your brain records the difference between then and now, and that recording is what you call a memory. The arrow of time is not a timeline. It is a hill. And we are partway down, catching the energy as it falls, using the gradient to build cities and songs and complex biological structures that could not exist without a flow of energy from order to disorder. We create local pockets of complexity by making everything around us messier. Life is an entropy machine. We eat ordered food and radiate disordered heat. We exist in the gap between the concentrated past and the diluted future. The problem with a hill is that eventually you reach the bottom. Right now, we are living in what astrophysicists call the stelliferous era, the age of stars. It is bright, it is warm, it feels like it will last forever. But if you map the full lifespan of the universe onto a timeline, this era is not a chapter. It is a camera flash in a dark room. The brightest stars are already dying. The massive blue giants that light up nebulae burn through their hydrogen in a few million years and explode. The mid-sized stars like our sun last longer, roughly 10 billion years, but our sun is already halfway through its supply. When it runs out, it will swell into a red giant, swallow the inner planets, and then collapse into a white dwarf, a dense cooling ember the size of the Earth that will radiate its remaining heat into space for billions of years before going dark. If you visited one 1 trillion years from now, it would be barely warmer than the void around it. A black dwarf. Almost no light. Almost no heat. Just a ball of crystallized carbon and oxygen. The mass of a star compressed into the volume of a planet. Sitting in the dark for an inconceivably long time. And there would be trillions of them. The galaxy would be a cemetery of dark spheres drifting through empty space, each one a memorial to a star that once lit up a solar system and made life possible on its worlds. Every sun that ever warmed a face will end this way. The red dwarfs will be the last to go. These are the smallest, dimmest stars in the universe, and they burn their fuel with extraordinary slowness. A red dwarf can shine for trillions of years. Trillions. but even they are not infinite. In roughly 100 trillion years, the last red dwarf will exhaust its hydrogen, flicker, and fade. And when it does, the stelliferous era ends, not for a while, permanently. No new stars will form because the gas clouds that make them will have been used up or dispersed beyond recovery. The universe will go dark. Not dim, dark. Every furnace in the cosmos will have burned its last fuel and shut down. But even in the dark, the universe will still contain objects. The white dwarfs will still be there, slowly cooling. Neutron stars will still spin. Black holes will still drift through the void, massive and patient. For a long time, these remnants will be the only landmarks in an otherwise featureless expanse. You might think they would last forever. They will not. Grand unified theories of physics suggest that the proton, the particle at the core of every atom in your body, in your chair, in the planet beneath you, may not be stable. It may have a half-life. If these theories are correct, then roughly 10 to the power of 34 years from now, matter itself will begin to dissolve. Not burn, not explode, dissolve. The protons inside every white dwarf, every neutron star, every cold dead rock drifting between galaxies will quietly decay into lighter particles and radiation. The white dwarfs will crumble. The planets will evaporate. Every solid object in the universe will unspool into a thin bath of subatomic particles and photons. Eventually, the only structures left will be the black holes. They will reign over the void for a span of time so large it requires numbers with hundreds of zeros to write down. But even they are not immortal. As we discussed earlier, black holes radiate. Hawking radiation bleeds them of mass, particle by particle, over eons that make the current age of the universe look like a single frame in a film. And when the last black hole finally evaporates in a faint burst of radiation, the universe will contain no organized structures of any kind. No stars, no planets, no atoms, only an ever thinner bath of radiation cooling toward absolute zero. This is called the heat death. But the cold is not the worst part. The worst part is what happens to the concept of happening itself. We usually picture the heat death as loneliness. You imagine yourself floating in the dark, bored, waiting for something to occur. But that picture makes a fatal error. It assumes you can still wait. It assumes that time still means something. Time is not a substance. You cannot pour a jar of it. In physics, time is a measurement of change. We define a second by the vibration of a cesium atom. We define a year by the orbit of the Earth. Time requires events. It requires energy flowing from one state to another. But in the heat death, the universe reaches maximum entropy. The temperature is the same everywhere. The energy is perfectly distributed. There is no hotter region and no cooler region. No gradient, no slope. Without usable energy gradients, no organized process can keep running. No engine can extract work. No computation can proceed. No chemical reaction can sustain itself. No biological system can maintain the difference between inside and outside that defines being alive. The universe does not end in darkness. It ends in sameness. A condition where everything is in equilibrium and nothing has a reason to change. Not frozen in the dramatic sense. Frozen in the thermodynamic sense. Think about what this means in concrete terms. You cannot build a clock, because a clock requires a difference between the energy source that drives the mechanism and the state that absorbs it. There is no difference. You cannot form a thought, because a thought is a sequence of chemical reactions, and a reaction requires a gradient between reactants and products. There is no gradient. You cannot perform a computation because computation requires erasing and rewriting states, and erasure requires dumping entropy somewhere cooler. There is nowhere cooler. You cannot do work of any kind, because work, by definition, is the transfer of energy from a region of higher concentration to a region of lower concentration. The concentrations are equal, everywhere. This is not a universe that is waiting for something to happen. It is a universe in which the concept of happening has lost its physical meaning. The film does not fade to black. The reel stops. And what remains is not silence. It is a permanent, featureless, changeless now that stretches in every direction without boundary and without end. And yet, in the middle of this forecast of permanent stillness, a physicist found something that should not exist. In 2012, the Nobel Prize-winning physicist Frank Wilczek asked a question that sounded like it belonged in a fantasy novel, not a physics department. Can matter organize itself into a pattern that repeats in time the way a crystal repeats in space? A regular crystal, a diamond, a grain of salt, is a structure where atoms lock into a fixed spatial arrangement. They tile, they repeat, the pattern holds. Wilczek wondered whether the same thing could happen along the time axis, whether atoms could lock into a temporal rhythm that just keeps going. The first experimental realizations appeared in 2017. Later, Google demonstrated time crystal behavior on a quantum processor. In specially prepared driven quantum systems, researchers observed patterns that repeat in time with a stable rhythm. The system is nudged periodically, but it responds at a different frequency than the nudge, and this mismatch is robust. It does not decay. It does not drift. It holds. Time crystals do not violate thermodynamics. They do not provide usable energy. They do not rescue complexity or life from the heat death. They are motion as repetition, not motion as becoming. Nothing is learned. Nothing is built. Nothing changes. In the frozen sameness of maximum entropy, there may still be patterns that tick. But do not mistake this for life. Life learns. Life adapts. Life changes. A time crystal only repeats. It is a heartbeat without a body, measuring a time that no longer carries any difference between one moment and the next. But if matter can get stuck in a loop, what about information? What about you? In certain cosmological models with enough time and suitable conditions, the shuffling of the cosmic deck forces the most unsettling coincidence imaginable. The mathematician Henri Poincaré proved that in a bounded system with a finite number of states, if you wait long enough, the system will eventually return to a state arbitrarily close to any previous arrangement. Think of a deck of cards. There are an enormous number of possible orderings, a number with 68 digits, but if you shuffle the deck forever, eventually you will deal the same hand twice. The same sequence, the same order. It is not likely on any given shuffle, but given enough shuffles, it becomes unavoidable. In the heat death, atoms drift randomly through the void. They collide. They bounce. They fluctuate. Most of the time, they produce nothing but noise. But over stretches of time so vast they require numbers with hundreds of zeros to express, random collisions will produce structure. Perhaps a rock. Perhaps a complex molecule. And in certain cosmological probability models, the statistics suggest that eventually, purely by chance, atoms will collide in the exact configuration needed to produce a fully formed human brain. Complete with neurons, complete with synaptic connections, complete with memories. Physicists call this a Boltzmann brain. It flickers into existence out of the void. It remembers a childhood. It remembers eating breakfast this morning. It remembers clicking on this video. It is absolutely convinced that it is a person living in the 21st century, but none of it happened. The memories are a random configuration of matter assembled by accident in a dead universe. The brain exists for a few seconds, thinks a few thoughts, and dissolves back into the vacuum. Many physicists treat the Boltzmann brain as a reductio, an argument against the cosmological models that predict it, rather than a literal claim about your identity. If your model says these brains vastly outnumber real biological observers, most physicists consider that evidence the model needs fixing. But the discomfort does not go away, because the argument cuts both ways. If the model is right, you cannot prove you are not one, and this is not a technicality. Think about what counts as evidence that you are real. Your memories, your sense of continuity, the feeling that yesterday happened and that you were there for it. But a Boltzmann brain has exactly the same evidence. Its memories feel just as vivid. Its sense of continuity is just as convincing. From the inside, real memories and randomly assembled memories are identical. You cannot check your memories against reality because the only tool you have for checking is more memories. If the model is wrong, we do not yet have a replacement that cleanly avoids the problem. One pillar remains. You have lost the sky, the solidity of matter, the explanation for your own consciousness, the arrow of time, and now the future itself. The last thing left to trust is the stability of the rules. The laws of physics, the vacuum beneath your feet, the reliability of the instruments you use to understand any of this. The final line of this descent puts all three under pressure at once. In physics, vacuum does not mean empty space. It means the lowest possible energy state of a field. The difference is critical. Imagine a ball resting at the bottom of a valley. Push it and it rolls back down. The valley floor is the true vacuum. Stable, permanent. You can build on it. But what if the ball is not at the bottom? What if it is sitting in a shallow dip, partway up the hillside? It looks stable. It feels stable. A gentle nudge and it settles back into the dip. But a hard enough kick sends it over the lip and crashing down to the real valley floor. This is a false vacuum. Stable against small disturbances. Catastrophically unstable against large ones. For decades, we did not know which kind of vacuum we live in. Then, in 2012, we found the Higgs boson. The Higgs field is what gives elementary particles their mass, and when we measured the mass of the boson associated with it, the number came out to roughly 125 gigaelectronvolts. This specific value lands in an uncomfortable range. Under current standard model extrapolations, and depending on parameters like the precise mass of the top quark, a Higgs mass near 125 appears consistent with a metastable vacuum. The ball may be in the dip rather than at the true bottom. If so, the floor beneath everything we have discussed is not guaranteed to be permanent. What happens if the ball gets kicked? At any point in the universe, a quantum fluctuation could push the Higgs field over the lip. If that happens, a bubble of true vacuum forms. Inside the bubble, the laws of physics are different. Chemistry does not work. Atoms cannot hold together. The bubble expands at or near the speed of light. You would never see it coming. One moment you are reading these words, the next moment the atoms in your body simply stop functioning. The bubble would consume the Earth, the Sun, and the entire galaxy, rewriting the local physics into a configuration where complex structures cannot exist. This is not an imminent threat. The probability of such a fluctuation occurring in any given region of space is extraordinarily small, and the current age of the universe suggests we are not on the verge of collapse. But the possibility is real in principle. It could have happened 1 billion light years away 10 years ago. If so, the wave of new physics would be racing toward us right now, and we would not know until it arrived. The universe may be permanent, or it may be a temporary arrangement that could be revised without warning, without appeal, and without a trace. But if the physical universe is this fragile, there is a question that sits beneath all the others. Why is it configured so precisely that we can exist in it at all? There are roughly 26 numbers that define how the universe works. The fundamental constants, the strength of gravity, the charge of the electron, the mass of the quarks, the speed of light, the cosmological constant. Nobody knows why these numbers have the values they do. They are not derived from any deeper theory. They are measured, recorded, and plugged into the equations. And the equations work. But nobody can explain why these numbers and not others. What we do know is what happens if you change them. Take gravity. Compared to the other fundamental forces, it is absurdly weak. 10 to the power of 36 times weaker than electromagnetism. That is a 1 followed by 36 zeros. Now, imagine adjusting that dial. Make gravity slightly stronger and stars burn through their fuel in millions of years instead of billions. Life does not have time to evolve. Make gravity slightly weaker, and matter never clumps together at all. No stars, no planets, no galaxies, just cold gas expanding forever. The same sensitivity applies to the strong nuclear force that holds atomic nuclei together. Even modest changes would prevent hydrogen from fusing into helium. The sun would not shine, water would not exist. The margins are so narrow that many physicists consider this a serious explanatory problem rather than a coincidence. The dials of the universe appear to be set to the exact decimal points required for stable atoms, complex chemistry, and biological life. The question is whether this is an accident, a selection effect, or something else entirely. And it is not just gravity and the nuclear forces. The cosmological constant, the number that controls the rate at which the universe expands, is tuned to a precision that physicists describe as absurd. If it were slightly larger, space would have expanded so fast that no structures could form. No galaxies, no stars, no planets, just particles flying apart in every direction forever. If it were slightly negative, the universe would have collapsed back into a singularity before the first star ignited. The observed value sits in an almost impossibly narrow corridor between these two catastrophes. It is not just that the dials are set correctly. They appear to be set at the exact edge of the range that permits complexity, as if someone found the boundary of the habitable zone and stopped precisely there. One major answer is the multiverse. In 1986, the physicist Andre Linde at Stanford showed that in many versions of inflationary cosmology, the rapid expansion of the early universe never fully stops. It ends in some regions, producing isolated pockets with their own physical constants, but keeps going in others, endlessly generating new pockets. If the constants are different in each pocket, then the range of possible universes is not a thought experiment. It is a physical process. But in a small fraction of these pockets, the numbers land in the narrow range that allows complexity. Stars form, planets cool, chemistry becomes possible. And in those rare universes, observers arise. Observers who look at their constants and say, how remarkable that everything is tuned for us. But there is nothing remarkable about it. It is a selection effect. You can only ask the question in a universe where the question is possible. This is called the anthropic principle, and as a logical structure it is sound. It explains why we observe these specific numbers without requiring anyone to have chosen them. But it has a cost. The multiverse is not observable. We cannot see the other rolls of the dice. We cannot test whether they exist. And the theory does not explain why the meta rules, the laws that generate the constants, are the way they are. It moves the question back one level without answering it. Why these laws? Why this dice? The floor drops again. You reach for solid ground and find another layer of questions underneath. There is a second answer. It does not require trillions of physical universes. It requires only one assumption. That computing power will continue to grow. In 2003, the philosopher Nick Bostrom published a logical argument that has proven difficult to dismiss cleanly. It is not a claim, it is a structure. He called it the simulation trilemma. Look at the trajectory of our own computing power. 40 years ago, the most advanced video game was two white rectangles bouncing a dot back and forth. Today, we have photorealistic virtual environments where millions of people interact in simulated worlds. If technology continues to improve, even slowly, then within a few thousand years we will have computers capable of simulating a human brain down to the individual neuron. And not one brain, billions. We could run entire civilizations inside a machine. Ancestral simulations, digital recreations of our own history, populated by conscious beings who do not know they are simulated. Bostrom offers three possibilities. 1. Civilizations always destroy themselves before reaching this level of technology. 2. They reach it but universally choose not to run such simulations. 3. They reach it. They run them, and they run billions. If option 1 is false, meaning we survive, and option 2 is false, meaning we remain curious, then we are left with option 3. And option 3 creates a mathematical problem. If there is one base reality and billions of simulated realities, and the simulations are detailed enough that the beings inside cannot tell the difference, then the odds that you are in the one original are vanishingly small. You are statistically almost certain to be inside a simulation. Bostrom does not assert that we are simulated. He asserts that one of the 3 propositions must be true, and that all 3 are deeply uncomfortable. The first says, we are doomed. The second says something fundamental about curiosity changes in advanced civilizations. The third says, you are probably not what you think you are. There is no comfortable exit from the trilemma. You can only choose which discomfort you prefer. Everything we have discussed rests on one final assumption. The assumption that science itself works. That when you design an experiment, the result depends on reality and not on how you chose to ask the question. That the atoms in the scientist's brain are not conspiring with the atoms in the detector. This assumption has a technical name: statistical independence. The physicist John Bell built it into the foundation of his famous theorem, a test designed to determine whether quantum particles truly behave randomly or carry hidden instructions. The experiments confirm the quantum prediction. Particles appear to be genuinely random, or at minimum correlated in ways that no local hidden variable theory can explain. But Bell's proof required one assumption. He assumed the experimenter is free to choose which setting to put on the machine, that the choice of measurement is independent of the thing being measured. Superdeterminism asks what happens if that assumption is wrong. What if the Big Bang set up the initial conditions of the universe so precisely that every choice you make, including the choice of which experiment to run, is pre-correlated with the result you are going to get? Think of a stage magician who asks you to pick a card. You feel free, but the magician has arranged the deck, the lighting, your angle of vision, so that you must pick the ace of spades. The choice felt genuine. The outcome was forced. If superdeterminism is correct, there is no randomness in quantum mechanics. The strange patterns we see are not properties of reality. They are artifacts of a universe that has been choreographed from the first fraction of a second. And if that is true, the standard assumption of independent experimental settings would be undermined. Science would not necessarily become impossible, but it would need a radically different foundation. One that accounts for the possibility that the observer and the observed were never truly separate. Superdeterminism is not proven. It is not refuted. It is difficult to test without challenging the very assumptions that underlie independent measurement. And there is an analogy from mathematics that is worth holding alongside it. Not as proof, but as a structural echo. In 1931, the logician Kurt Gödel proved that in any formal system complex enough to perform basic arithmetic, there will always be statements that are true, but cannot be proven within that system. Physics is not a formal axiomatic system in the way Gödel's theorem requires, so the theorem does not directly apply to the laws of nature. But the shape of the idea resonates. We use mathematics to describe the universe, and we already see places where the description hits walls. Gravity and quantum mechanics refuse to unify despite a century of effort. Dark energy resists explanation. Whether these are merely hard problems or symptoms of something deeper remains an open question. But the possibility that some truths about the system are inaccessible from within the system is at least consistent with what we observe. We started with the empty sky. We discovered that we fit the profile of a grabby civilization, the kind that paves over galaxies. But buried inside that logic was an assumption we never tested. The assumption that we will survive long enough to become grabby at all. Look at the timeline. We have had nuclear weapons for 80 years. We have had synthetic biology capable of engineering pathogens for less than 2 decades. We have had AI systems with increasingly broad reasoning capabilities only very recently. These are not mature technologies woven into a stable civilization. These are new capabilities in the hands of a species that has not yet demonstrated it can manage them over the long term. And history shows a pattern. We deployed nuclear weapons before we modeled fallout. We sprayed chlorofluorocarbons for decades before we noticed the ozone hole. We burned fossil fuels for a century before we measured the temperature. In every case, the capability arrived first and the understanding came later. The gap between what we can do and what we understand about what we are doing is not closing. It is widening. And it is in that gap that the filter lives. There is a heuristic called the Lindy effect. It says that for non-biological systems, future life expectancy is roughly proportional to current age. The pyramids have stood for 5,000 years. They will likely stand for 5,000 more. But a technological civilization capable of destroying itself is very young. Ours has existed in its current form for less than a century. According to the Lindy heuristic, we are in the infant mortality phase, the period of highest risk. The math of the Great Filter allows for a possibility that is easy to state and difficult to sit with. Most civilizations that reach our level of technology may not become interstellar. They may become extinct. They discover a capability too powerful to control, a self-improving system, a synthetic organism, a weapon that cannot be recalled, and they sterilize their own planet before they launch a single colony ship. In our observable region of the cosmos, no civilization has left a visible trace that our instruments can detect. We are attempting something that, as far as we can tell, has never been done. Maybe that is because we are first. Maybe it is because this is the step where most species fall. The two explanations are not mutually exclusive. We may be both early and fragile, first to arrive and statistically unlikely to survive the arrival. The silence in the sky is not a single message. It is a question with two possible answers, and we do not yet know which one applies to us. 6 pillars, 10 fractures. You have spent nearly 2 hours watching each one crack. The sky emptied. Matter dissolved into information and mathematics. Consciousness became the one thing physics can describe from the outside, and cannot explain from the inside. Time lost its arrow. The future collapsed into sameness, and the floor turned out to be a ledge that quantum mechanics could kick out from under you without warning. And you are still here. You did not stop. You did not look away. That is not courage. It is something more fundamental than courage. It is a property of the very thing we could not explain. Consciousness. The hard problem. Physics can map your brain from the outside, but it still cannot explain why there is an inside. In 1974, the philosopher Thomas Nagel asked a question that science still cannot answer. What is it like to be you? Not what your brain does, what it is like. And yet there is an inside, right now, reading these words, weighing them. Right now, you're experiencing understanding. Not comfort, not panic, something that does not have a clean name. A sense that the world is radically stranger than you assumed 2 hours ago. That the gap between what you experience and what the equations describe is wider than anyone told you. And that this knowledge, unsettling as it is, has changed the quality of your attention. You are not less present than you were before. You are more present. The room has not gotten smaller. Your awareness of what the room is made of has gotten larger. This is not consolation. We are not telling you that everything is fine. We are telling you that the act of understanding, even when the content of that understanding is disorienting, is itself a form of presence that the universe cannot explain and apparently cannot do without. We made a promise at the beginning. We said that by the end of this video, the room you are sitting in would feel different. Not because anything changed, but because you would know what it is made of. The table under your hand may not be substance. It may be a ripple in a mathematical structure that has no physical substrate. A pattern of information encoded on a boundary you will never see. The air around you exists in a vacuum that, under current models, may not be in its lowest energy state. Many of the equations behind the light by which you see this room do not contain the everyday arrow between the direction you remember and the direction you cannot. And the fact that you are aware of any of this, that there is something it is like to be you, sitting in this specific chair at this specific moment, has no address in any physical theory we have ever written. These ideas are not hidden. They are not forbidden. They are published, debated, and available to anyone who looks. But they are difficult. They are speculative in places and established in others, and the line between the two requires care that most public conversations do not provide. Most people live entire lives without encountering a single one of the questions you have just asked. Not because the questions are obscure, because they are uncomfortable, and because the answers where they exist do not fit on a bumper sticker. The world did not become more dangerous in the last 2 hours. It was always this strange. It was always this precarious. It was always this beautiful in its refusal to be simple. The only thing that changed is that now you know. And that knowledge is not an answer. It is not a map with a destination. It is a different way of looking. A lens that once focused does not easily unfocus. 6 pillars, 10 cracks. You started this video trusting the sky, the ground, your own mind, the flow of time, the openness of tomorrow, and the reliability of the rules. You are ending it with each of those trusts marked by a question. Not destroyed, marked. The questions do not close the door on reality. They open windows that were painted shut. And through those windows, the view is not comforting. But it is wider. It is stranger. And it is more honest than the view you had before. The room is the same. You are not.